All right, so before we get going, a couple of things I want to mention. So if we go to Canvas, we kind of see we got these final assignments. Hopefully, this fourth Excel and fifth Connect have been out there a while. If you've been kind of chipping away at them, you could all easily already have had them done last week with the material that we covered. It was kind of giving a little bit more time there. And then in kind of the final Connect and final Excel, which are due that Monday of finals week. Hopefully you get them done before that. I think they probably take a little less time than some of the other assignments. Remember, I dropped the lowest of each type, so you can miss one Connect and one Excel, and those get dropped, right? Or if you do them all, I just drop your lowest score of those. Okay. So we've got those sitting out there right now. As soon as the due dates pass, I'll try to get those Excel 4s graded relatively quickly, so I can start to update scores. We'll also, as I say this, forgot to start it, be using iClickers for the last time today. So I'll get your lowest, I think it was 2 dropped as a syllabus stated. It was either 2 or 3. I can't remember what I had it set in the syllabus as. Whatever it states, that's the number I drop. And we'll kind of give you what your iClicker grade is. Once we start to get those connecting Excels, I'll get those updated quickly. And then Wednesday, I'll bring this Excel file and put it up on Canvas, which I'll call like figure out your grade tool, where you can kind of plug in different values for the final and figure out what you need in the final to get whatever your desired grade is in the class, okay? Based off of everything that you've done up to this point. Now, it'll be a little bit off if you do it this week because you still could do, the final Connect and the final Excel, but it'll give you a pretty good idea of where you're at, okay? I believe that should be everything here. I put up an announcement as well. Number 4 on the Excel, I had changed the example because we ended up working through the one that I had originally had on there in class, so I had to switch it out. And I forgot to update the language in part A. So the original paragraph could have had everything laid out correctly. There was a mention about differences between males and females, and it should have been just the differences between 2012 and 2005. So I've updated the language there. The Word document is correct now, but I just wanted to kind of make sure that, if anyone was kind of confused by that, kind of wanted to clarify, okay? Other than that, any questions for me before we kind of jump into things here? So Wednesday, I'll bring that figure out your grade tool, do a little bit more regression stuff, but we may even start to do a little exam review on Wednesday. And then next Monday, that's all we'll do. Kind of when we meet, you don't have to show up if you don't want to. Like I said, today's the last day I'm using iClickers, but I'll just be doing exam review next Monday, kind of leading into the exam. I think that should do it for me, unless there's any questions here. Kind of get things settled here. So we left off, I was showing you how to run these regressions in Excel. I then said, if we wanted to, we could do this by hand using these formulas. Excel does this for us, so we don't really have to go through all these steps. Right? We don't have to walk through all these steps. But Wednesday, if we have a little time, I might kind of show you that it reproduces the same answers. But for right now, it's not overly important. We then started to talk about multiple linear regression, where I can include several variables there on my right-hand side. So I'll show you how we do this in Excel today, and we'll talk about the final kind of topic that this brings up, which is, let's say I was to estimate this regression of crime, right? I want to predict crime. I'm going to try to use police force expenditures and unemployment to do so. Okay? So it ends up being true. If I think about, if I was to run a simple linear regression, and I was kind of naive and said, okay, I just want to try to predict crime rates based off of police expenditures in a county or city, whatever level this is at. Well, if I run this regression, what I end up seeing is that my estimate for that slope, or that relationship between police force expenditures and crime, that this is actually positive. Now, this seems kind of counterintuitive. If I spend $1 additional on my police force, this slope coefficient tells me the expected increase or decrease in crime rates. Now, we would probably expect that the size of that effect to be pretty small, like $1 isn't that much more. But if I know the effect of $1, I can find the effect of 1,000 by simply multiplying that by 1,000. Right? But why would it be positive? Why would spending another dollar on my police force increase crime rates? What kind of areas do you think are likely forced to spend more on their police force? Places that have conditions that are conducive to higher crime rates. So we're really picking up the effects of all those other things. So what we want to try to do is start to add in maybe some of things that would capture the economic conditions in that area. So areas that have lower incomes, higher unemployment rates tend to have higher crime rates as well. And that's likely correlated with them spending more in their police force. So as I add in more additional control variables, the interpretation of my coefficient is exactly the same. It's still the effect of a $1 increase in police expenditures would change the predicted crime rate by whatever this B value ends up being, that Excel spits out at me. But now I can add the phrase, holding all else constant in my regression. So it's like saying two counties with the exact same unemployment rate, but one of them spends $1 more on their police force. What would that impact be on crime? And as soon as I include an additional control for the socioeconomic kind of status of that county, I'll see that my estimate actually flips sign. So why does it do that? Well, I'm going to skip all the way down to here real quick because I have a slide that I like here. So what's going to end up happening if we omit important variables from our regression? So let's say I try to estimate this very simple linear regression, only including that variable x1. If there's another variable x2 that's important for predicting y, but I leave it out of the regression, through a bunch of fancy math, you can prove that the estimate that I see, so this is like B hat, I just stole this from a textbook that was a little more technical. So this B hat will capture the true effect or the true relationship between x1 and y, but also this additional kind of bias component. I'll talk a little bit more about this in a second, but for now, all we have to know is that this bias is going to exist if I don't include x2 in my regression. Okay? So go back up and talk about a few more things, but we'll return to that eventually. Okay? So what I'm going to do then is try to control for as many things there on the right-hand side as I can. I'm going to start including as many x variables on the right-hand side to help predict y as I possibly can. Well, now, instead of just figuring out what the value of the intercept and the value of the slope are, I need to know the slope or that coefficient between every x variable and y, right? So I now have n different things, n different coefficients I need to find the value. So before, we said we would take a derivative in respect to both a and b, the intercept and that slope coefficient. We then had two equations, two unknowns we could solve. Now I'm going to have n, I guess, plus 1, right, plus the intercept, n plus 1 equations, n plus 1 unknowns. I can still solve for it. It's very complicated, right? You need to use matrix algebra or linear algebra. It's a nightmare, but we don't have to do that. Excel can do all of that math behind the scenes for us, okay? But the interpretation will still be the same. It's just now we have this added benefit where we can say, holding everything else in this regression constant, which is a lot more powerful. Hopefully, when we're through some examples, we'll see how much more powerful this. You can kind of hopefully have some good examples of why this is more powerful. So as we include these additional variables on the right-hand side, we're also going to introduce another statistic that we'll start caring about, which is the R squared. Okay? So the R squared tells us the percent of the variation in our Y variable that we can explain with our X variables. Right? And not really, technically, it's not the percent. The way that it's usually spit back out of us, it's the proportion of the variation that we can explain. So if we want to make it a percentage, right, we just move the decimal 2 places or multiply by 100. So what it is it's measuring that variation in our dependent variable that we can explain with the X variables that we've included. Okay. So another way of thinking about it is here. It's the ratio of what we call the sum of the squares from our regression. So this is like, use all the variables that we included on the right-hand side, use their coefficients to come up with predictions for Y. And I'll show you what this looks like with some actual numbers in Excel here in a little bit. But we're going to have all these predictions for every single observation, what the Y value should be. This will kind of represent the variation that we're explaining with whatever variables we've included on the right-hand side there, because those are the only ones that show up in our prediction. So here's like the variation explained by my predictions divided by the total variation that existed in the actual y values. Now, my actual y values are going to be a little bit different than my predictions. We said the difference between them was kind of that error term. So the kind of ratio of the variation in my predictions to the variation in the actual y values, that tells me how much of that variation in y I'm explaining with my x variables or explaining with my predictions, if you want to think about it that way. Okay. So in practice, we'll just look at r squared. We don't have to worry about the sum of the squared from the regression or the sum of the total sum of squares. We don't have to worry about that. Something that's going to become an issue, though, and I kind of already alluded to it with that bias component in our estimate, is when we look at these results, we need to be very careful that we don't just kind of take them as causation, that there's still just evidence of a correlation between this x and y variable. Okay? So I already kind of mentioned this police force expenditure example, how as soon as I included the unemployment rate, it kind of flipped the sign, right? So I go from this naive regression to controlling for the socioeconomic status, and it would flip the sign of that coefficient, potentially. Right? Or maybe another example, it would be good to understand this. So let's look at birth weight, and then what we call a dummy or an indicator variable, which is just a 1 or a 0. So here, smoking while pregnant was a 1 if they smoked while pregnant, 0 if not. I think we did this example last class, right? So now a 1 unit change would just be going from the group that's a 0 to going to the group that's a 1. So a mother that doesn't smoke while pregnant to a mother that does smoke while pregnant would decrease birth weights by whatever that slope coefficient is. And I say decrease because from last class we know it was negative. And just intuitively, I think we know it's lower birth weights means poor health outcomes for the baby, which we would imagine smoking while pregnant would have worse outcomes. Right? So this is negative. Does that really mean smoking while pregnant is really causing these huge decreases in birth weight? Well, I mean, we know it's not good for medical science, right? But in terms of impacting birth weight, what do if we start to think, what do we not include in this regression? A lot of other things. So mothers who smoke while pregnant, if we look at the data, and maybe this is somewhat stereotypical, but it does play out in the data, we just see that they come from lower income classes and have lower levels of education, which makes sense. The lower education, maybe they're just not aware of how bad it is. Maybe they're ignorant. Lower income. If you have lower income, you're just less likely to have availability to good health care, to high quality foods or vitamins while pregnant. And so these other things, right, low income, low education, that are correlated with being more likely to smoke while pregnant, we might actually be picking up the effects of those in our coefficient if we leave those things out of the regression. Now, if we include them in the regression, now it's like, remember, holding those things constant, okay? So it doesn't matter how they're related to smoking while pregnant because we've held them constant. But if we leave them out of the regression, anything they're correlated with that we leave in the regression, those coefficients might pick up some of the effect of those other things we left out, like low income, low education levels. So if you actually look at the data, yes, smoking while pregnant still has a negative coefficient. It's still bad for birth weights, but it falls like by 80%. Like the size gets a lot smaller. So it's still bad, but right, a lot of what it was picking up when we used this really naive regression was all these other factors that are more likely to lead to lower birth weights as well. So, another good example, if you had data like this, autism and organic food sales, this is going to have a very significant coefficient and be very strongly positive, right? But I don't think anyone's going to argue organic food sales are causing autism rates to increase, right? It's more likely that there's some outside factors like more of an emphasis or focus on health that's driving both of these things that we've left out of the picture here. Okay. So what can go wrong here? Well, sometimes, maybe it's that we have our regression flipped. We won't spend a lot of time on this. This is kind of like simultaneous equation modeling. That would be like probably the next level of stats, maybe even 2 levels above us, what we're doing. But the one thing that we can understand is if we leave this other thing Z, I called it X2 before, out of our regression, right? And Z is driving both X and Y. So this was the idea that temperature was driving up murder rates and ice cream sales. The ice cream sales and murder rates that, they were correlated, but they're not causing each other. Right? It's this outside factor Z. So kind of the old, I don't know, newspaper kind of cartoon. I used to think correlation implied causation. Then I took a statistics class, so now I don't. Well, it sounds like it helped. Well, maybe, right? Because maybe it wasn't that taking the class helped me understand this. Maybe it was some outside factor that led to me taking to the class and led to me understanding this. Right? So I think I've got a good example for this, and we'll kind of think about this bias. So I've got this GPA omitted variable data up in the in-class data folder on Canvas. So I'm going to get rid of this SAT squared term for right now because we're not doing anything with this in this class. This is just a data set I had that I was using for multiple classes or kind of as a toy example. So we'll get rid of that. So the first thing I'm going to do is just recall, how do I run a regression? So hopefully we've got that analysis tool pack added in. Just a reminder, on a PC, file, options, add-ins, manage my add-ins, make sure the analysis tool pack is checked. On a Mac, you go like all the way to the top, even if you don't have Excel, but it's like tools, you then see an add-ins option, click on that, and then you can get the analysis tool pack. Once you have that selected, under the data tab, we have this data analysis option, all these different things. We want to do regression. Our Y variable, right? Oops, I'm going to select as my college GPA in this data. Okay. So I want to try to predict GPAs, and I'm interested in the relationship between GPAs and whether or not the student is a student athlete. Right? So these are college students, this data set that I have. I selected the label, so I make sure that's checked, and then I hit OK. So it spits this out in a different sheet. We'll zoom in so we can see this a little bit better. So just by including the variable of student athlete, I'm only explaining the proportion of the variation in GPAs I'm explaining is 0.008, so 0.8%, right? So not very much, right? There's a lot of other things that are probably a lot more helpful in predicting GPAs. Right? So what we just did there was, as our Y variable, we had GPA, and we were trying to predict that using this indicator variable, which is a 1 if the student was a student athlete, 0 if not. So you might, the question might be, is being a student athlete a good or a bad thing for a college student? So I remember when I was an undergrad, I had a class with this football player at Purdue, and he would go over his schedule. I think we had a group project, and so he had to like break down when we could meet. And it was literally like every minute of the day he had was booked. Like he had film, weight room, practice. Like I think I had class in the fall. So it was a particularly busy time for him, right? So all these additional requirements, maybe it detracts from how well you're doing academically. But also, there's a lot of freshmen who come into college with no structure, and a student athlete coming in with, has to be taught structure and time management skills right from day one, right? And so maybe there's these added skills that being a student athlete helps you develop, and that actually leads to you becoming, doing better academically. So we might be interested in this question. So we run that regression. We're not explaining much of the variation yet, so there's probably a lot of other things we should control for. And we see that being a student athlete has this huge negative effect on GPA. I say huge. The interpretation here, remember, it's a 1 unit change in the X variable, but that's X variable is just a binary, a 1 or a 0. So the 1 unit change is going from the 0 group to the 1 group. So being a student athlete relative to not would decrease GPAs by about predicted GPAs by about 0.28, which GPAs are on a 0 to 4 scale. And honestly, hopefully we don't see a lot of GPAs like below 1 or 1.5, right? So that's a pretty sizable impact in the relevant kind of range of values. All right, there's probably a lot of other things, especially if this data came from like large D1 universities. If I've got football and basketball players in here, there's a lot of money being made off those programs. We look at the data, sometimes schools are a little bit more lax on, that #1 star quarterback recruit in terms of their standards to accepting them as opposed to their average student body. Right? So maybe there's other things like their intellectual ability that might be correlated with being a student athlete, but also correlated with their GPA. So we want to control for maybe like their intellectual ability. Now, there's no perfect measure of this, right? It's very hard to do. But one thing that we could use, that's an okay, not everyone's a great test taker, but SAT should capture fairly well, on average, should capture kind of what the academic ability of these students are. So we'll go to data analysis, my regression again, same Y variable. It's just now I can select multiple X variables. So I'm going to select SAT and athlete, Control Shift or Command Shift on the Mac, hit the down arrow, selects all of my data. I still have my labels selected, and I'll hit OK. All right. So I'll zoom in so we can see this a little bit better. Now, just by including that SAT score variable, I've increased my R squared from 0.008 to 0.16. So SAT scores apparently are very useful in predicting GPAs, right? They increased the amount I can explain, the amount of the variation in GPA I can explain by about 16%. Okay? So now when I go down and look at this athlete variable, right, I see that it's now still negative, but it's negative 0.05. So it's fallen by quite a bit, because now I can say the effect of being a student athlete decreases GPAs by about 0.05, or predicted GPAs, holding constant the SAT score of the student. So two students who come in with the exact same SAT score, but one of them is a student athlete, we would predict their GPAs would be about 0.05 points lower. It's not near as large of an effect as from that naive regression. And that's because the naive regression had this bias component. But as soon as we include that variable that we left out, this whole bias component goes away. So as soon as we include that X2 variable, or that, in this case, SAT scores in our regression, we eliminated that bias from the estimate that we see in Excel. Okay. Any questions up to this point before I keep moving? So if we remember from last class, when I see these estimates from Excel, they're like sample coefficients, just like when we had sample means. And they should be centered around whatever that true relationship is. Now, we said we always have the null hypothesis that the true relationship is equal to 0. So we always start out assuming that there's no relationship between our X and Y variables. If I then see a coefficient estimate that leads to a p-value that's less than alpha, it's a two-tailed test, so technically if I'm drawing it out correct, my p-value would be the area in both tails. But if that p-value Excel tells me is less than the alpha, then at that level I can reject the null. But if I'm rejecting the null, I'm rejecting that there's no relationship, which said differently, I'm saying that there is a significant relationship. Okay. So we're going to look at our output. And here, if we look at the p-value for being a student athlete, can I reject that null hypothesis at any of my conventional levels? Well, 90, 95, 99% confidence levels, we had alphas of 0.1, 0.05, 0.01. My p-value is not less than any of them. So I fail, right? I would fail to reject the null, which if I fail to reject this null, I can't say that the relationship between being a student athlete and GPAs is anything different from 0. I'm failing to reject that, okay? So I can't say that being a student athlete has any impact on GPAs here, at least from the regression that I just ran, okay? Now I can look at the other variable of SAT score, 5 times e to the negative e, and e, it's to the 10 to the power of negative 159, which means move the decimal 159 places to the left. So this p-value, for all intents and purposes, is 0. Right? If I have a p-value of 0, that's definitely going to be less than alpha, right? So if my p-value is less than alpha, I reject. So for SAT, I can reject that there's no relationship, or said differently, I found significant evidence that there is a relationship between SAT scores and predicted GPAs. So we can use those p-values to determine if these sample statistics we found are actually, significant, or what level of confidence we could reject that null that there's no relationship. And I can do that separately for both these variables. And it's also adding in, the interpretation. We can always say holding the other variable constant. So the way we would interpret this SAT score is for every 1 point increase in the SAT score, that would predict that student's GPA would be about 0.0019 points higher, holding constant their student athlete status. Well, that's pretty small, but that's the effect of 1 point. A 1 point increase on the SAT is not that much, right? What's probably more relevant would be like, well, what if a student did 100 points better on the SAT? Well, if we know the effect of 1 point, we would just be multiplying that by 100. And there, if I increase my SAT score by 100 points, my predicted GPA would go up by about 0.19. That's a little bit more sizable effect. That makes a little bit more sense here. Okay? But starting out, because the units of our SAT were just in points, we got the effect of a 1 point increase. Okay? Any questions on anything up to this point? Okay, so we'll do one more regression here, and then I think I'll show you one other data set. Okay. So I've got my data analysis regression. I'm going to try to predict GPAs, but now I'm going to throw every variable that I have at this regression. So this verbal math was like some verbal math test. They had some numerical measure of how well the student did. High school rank was where you rank in your high school. Gender, racial demographics, total credit hours taken at the point GPA was measured, and then their high school size, which if I remember correctly, this is in the hundreds. Would that make sense? So that would be a really small school. I don't think it necessarily matters for what we're doing. This was either in hundreds or maybe 200s or 500. So right, the unit measure here isn't like a one student, right? It's like some continuous measure of high school size. So we'll select all these variables, right? Just Control Shift, Command Shift on a Mac, hit OK. And now we've got a lot more powerful of a result if we want to understand the relationship between predicted GPAs and being a student athlete. First of all, we've increased the R squared, or the amount of variation in GPAs that we can explain. We can now explain 30%. Now, this is still far from explaining 100% of the variation, but we've at least increased it by quite a bit. And now when I want to interpret that athlete variable coefficient, this is the effect of going from not being an athlete to being a student athlete, right? Going from the 0 to the 1 group, holding everything else constant. So this is like two individuals with the same SAT score, same score on this verbal math test, same rank in their high school, same, either both female, both male, either, same, race identifier, whatever it ends up being, same total number of credit hours taken, same high school size, but one of them is a student athlete, then we would predict that that student athlete's GPA is about 0.17 points higher. Right? So as we start to account for all these other factors that we know matter, not only did the sign of the student, not only did it get smaller, but the actual sign of the effect of being a student athlete has flipped. Right? And that makes sense. Like once we control for all these other factors, two otherwise identical students, but one of them is a student athlete, apparently there must be some time management skills or something that's learned that kind of help increase that student's GPA. Or you could be cynical and say that the professors are forced to give a higher grade, although from my experience, that's never been something that I've been approached with. So, and the p-value is basically 0. So we can now say it definitely has a significant relationship, right, between athlete and GPAs, being a student athlete. Any questions over anything up to this point? Got two more things in this data set I want to show you. Okay, so the first one that I want to show you is, well, let's say I asked you what variables in this regression are significant, right? Or which ones can we reject the null at for different levels of confidence. So for right now, I'm just going to say alpha is 0.1 I'm going to put that up here. And then I'm going to make a column, which is my rejection decision. Okay. So what I'm going to do is I'm going to go through for every single one of these variables and determine whether or not I can reject the null. If I can reject the null, then I'm rejecting that there's no relationship, or I'm saying I found evidence that there's a significant relationship. If I fail to reject it, then I can't say that there's any significant, or that, I would say that there's no significant relationship, right? Because I can't reject that that slope coefficient is 0. Always a two-tailed test. But the thing is, when we use Excel to do this, if you were doing this by hand, when you find this area, you'd have to multiply it by 2 to get your p-value. Excel always does that. So it's already been multiplied by 2. Yep. Yeah, in practice, like you can do some wild things with the regression. Like you don't have to assume that the coefficient is, I might be going too far. So this is what we will always use in this class, right? You can do like, is the coefficient greater than 0 or less than 0? It presents a lot more challenges. You can also actually test for whether or not it's like not equal to some factor like 2 or 4, right? Or whatever you'd be interested in. But for us, we're always going to keep it as 0. So yeah, but yeah, it would always be a two-tailed test there. So one thing I showed you with hypothesis testing that would come in handy here, and you could do this by hand, right? I could look through here and say, okay, which of these has a p-value less than 0.1? Well, all of these that have e to the negative, that just basically means 0. So I'm going to be able to reject the null for all of these p-values where I see an e to the negative whatever. So I can reject the null here, here, here. So all 3 of these first variables, I would say have a significant relationship with GPA. The verbal math score just barely does it, right? It's just barely above 0.1. So I'd actually failed to reject the null there at the 90% level. And I can't say that there's a significant relationship between GPAs and this verbal math score. So if I'm at the university and they're using this test, I look at them and say, yeah, this doesn't have a whole lot of predictive power. There's no reason to make them take this. Right? Now, I could say that, but what's also true, this isn't significant. I couldn't say that it has a significant relationship at the 90% level, but I could at the 89%. So is that really that much worse than if the p-value was just a little bit smaller? Probably not, right? But it doesn't make our kind of benchmark kind of threshold. Then for these next 2 variables, it looks like they have a significant relationship, kind of indicator on whether or not the person's white. That p-value is huge. That apparently doesn't have any predictive power. And then for these next 3, we've all got p-values less than alpha. So I would say there's a significant relationship between these 3 variables and predicting GPA as well. Okay? So I can do that by hand, or to prevent myself from making mistakes, because I've seen people do it a lot, right? You might look at the p-value and it's 0.00 or 0.005 and you think it's 0.05 instead, or vice versa, or you see the e to the negative, excuse me, and you think, oh, 5, the p-value is 5, that's not less than any alpha. Well, no, it's not 5. First of all, a p-value can't be outside of 0 and 1. It represents a probability. But it's easy to make that mistake sometimes when you're looking at it in scientific notation. So we could use this if statement and say, look, if this p-value on the variable, the p-value associated with the coefficient is less than this alpha value that I've set, comma, that shows me I can reject the null, or that there's a significant relationship between this x variable and the y variable we're trying to predict. If it's not less than alpha, I would say I don't have evidence to reject the null, which is that there's no relationship, or that's not a significant relationship between that x variable and our y variable we're trying to predict. Okay. So once I copy this down, it'll use the p-value for the next variable, and so I can make rejection decisions very quickly for each of these. However, if I copy this down, what's one thing that I don't want to change? I always want to compare to whatever alpha I'm setting, so we'll freeze that cell reference. Okay. Now, I'm going to drag this down, and I get the same decision as eyeballing it, which is that for this verbal math score and that white indicator, those are not significant relationships, but every other variable, I can reject the null, or I found evidence that there is a significant relationship, at least at an alpha of 0.1. Okay. Now, I don't think we have, first of all, are there any questions on that before we keep moving? You know, one nice thing about setting it up this way, like not necessarily for this class, but like if you were doing some type of regression in the future, is let's say I had a p-value that was like 0.07, okay? So at the 10% level, it's significant. But then if I wanted to start to change things, maybe I want to be able to say with 99% confidence, well, now I get it, and it flips my decision, right? So it's kind of nice to use a cell reference there, so I can look at different levels of confidence pretty quickly, or different levels of significance fairly quickly. Okay. So any questions on this part before we keep moving here? All right. So the next thing I wanted to do, well, we can use the same output. So let's say, let's think about what we're doing here. Once I have these values in Excel, if I want to come up with predictions for GPA, I'm going to have a value here for the intercept. I'll have a value for that first slope coefficient on, I think it was athlete, then another coefficient estimate for SAT, all these other variables. Well, for all of these slopes, or all of these intercept or slope coefficients, these are going to be numbers. And then for a hypothetical person, I could just plug in whatever their X values are and figure out what their predicted GPA would be. Okay? So I'm just using that linear regression. I mean, it's a linear equation, right? So I could just take a hypothetical person's values for each one of these X variables, multiply them by their associated coefficients, and then add them all up, and that would give me my prediction. I also have to remember to add in the intercept or the constant as well. Okay? But that's all we're going to do here about what I'm about to show you in Excel. That's really all I'm doing. Right? So I've got all these coefficient values. So I'm just going to create a column over here, which is take the coefficient and multiply it by X for this hypothetical person. Whoops, I did not want to do that. So this is like my hypothetical person I'm trying to estimate this regression for. So I'm going to delete these columns because we don't need them, and that way I can show you everything. There we go. So all I'm going to go through and do is take every single coefficient and multiply it by, actually, I forgot a column here. I want to show it to you in steps. So here's my hypothetical person, right? And here's my coefficient multiplied by that person's hypothetical person's value for X. So for this person, we'll say, what if they had a 1200 on the SAT? Once again, I can't show you all this, so I'm going to actually, unfortunately, make this just a little bit smaller so that we can hopefully fit. Oh, did that not change it? 50. So we can see all this at one time. So I think that's helpful. So a 1200 on the SAT, let's say they weren't a student athlete. Their verbal math score, if you look at the values, this was kind of like between like 0.5 and 1 point something. So we'll say they got like a 0.8 on it. Their high school rank, we'll say they were 15th in their high school. Say they were male, so we put 0 in here. They're white, which means that black would be a 0. They've taken 55 total credit hours up to the point where their GPA was measured. And their high school size, like I said, I can't remember exactly what the scale is here, but 4.5 is kind of the middle of the road. So we'll use that as kind of their hypothetical high school size. So what I'll do is go through and take this hypothetical person's value for X, multiply it by the coefficient on that value, right? Because it's telling me the effect of a 1 point increase in SAT. Well, if this person has a 1200, then the total effect of that would be 1200 times that 1 point effect. Okay? And then for the next one, we would take the student athlete coefficient multiplied by either a 1 or a 0. If they're not a student athlete, this coefficient doesn't get added in. If they are, right, if this was a 1 times this, it will get added in. So we're just going to go through and do this for every single variable. All this is doing is multiplying our coefficient by the hypothetical person's value for X, right, for whatever variable X that is. We then said, once I do that, I just want to add them all up, right? I've got an addition sign in between each one of those sums. So I'm going to add all these up. And then I need to not forget, oh yeah, I've got this intercept here as well that I need to add in. So I'll add in that coefficient on my intercept or on my constant as well. Okay. So this person's predicted GPA would be 3.11. Okay. So this is how I come up with predictions for any hypothetical combination of these things, right? So if I like ran this regression, then someone came to me and said, okay, going into, if I have this individual, could you predict what their GPA was going into college? I could plug all those values in and figure out what their predicted GPA would be. Okay. So if I'm like an admissions department, maybe this is something I might want to consider doing. I'd have a lot more data than just what we have here, right? Because all their applications would have additional data where I could really come up with predictions for how successful each one would be. Now, for any one person, I can come up with this prediction and it might be off, right? Maybe there's some other things I didn't capture here, like, I don't know, working a second job. That takes a lot of additional time. Maybe they're caring for, you know, someone who's sick, like a sick parent or something. So maybe their actual GPA ends up being lower, but it's because I didn't have all this additional information, right? But with the information that I have, right, based off the data that based off my data set, their predicted GPA would be 3.11. Okay. Now, another way you could do this, I think it's easier, is notice I left this row for the intercept blank, but what's one way I could make sure I just add this in? Just always put a 1 there. That way, when I multiply the coefficient by the hypothetical person's x value, well, it always is just going to be the constant or the intercept there. Now, instead of having to use the sum and then going back and adding the coefficient, now I could just take the sum of this entire column. Oops, except where I switched out. There we go. And get the exact same value. Just two different ways of doing the same thing there. Any questions on that? Okay, so we can come up with predictions. We talked about scaling the effect. If I know 1 unit, I can scale it for, you know, the effect of 100 or 5,000 or whatever units I want. We talked about making rejection decisions based off of this regression. We also talked a little bit about kind of this omitted variable bias. So I've got one other example, and I think we'll save this stuff for next class. So I've got one other example, which is, oh, I think I already have it open. I put up kind of a slightly new file than the one we have been using with COVID, which is called COVID regression data. Right? So if we use this file, I merged in some additional information. This makes a little bit more interesting of a regression, and it allows us to think about that bias component a little bit more as well. Okay, so maybe I'm interested, and I think I was using this earlier. So let me shoot. I'll download the one off Canvas because I want to make sure I show you a few things that I think I already changed in that one. So if we go to Files, in-class data, COVID regression data. So I'll download this, and now we'll start out from scratch. All right, so I have the cases, number of cases per person here, and this is all at the county level. So I divided the number of new cases from, I believe, June to October in these counties by the population to get the cases per person, and then I multiply it by 1,000. So this is like the number of cases that they had, new cases per 1,000 people in the county. So we've already kind of factored in the population, which is nice. And maybe I run a real naive regression, which is I want to be able to predict the number of cases per person in the county using the percent vaccinated of that county as well. Okay, so select that percent vaccinated. I'm then going to hit OK, and I get this output. Right? So the way I would interpret this is that for every additional unit in my X variable, which here my X variable is measured as the percent of people vaccinated. So a 1% increase in the people that are vaccinated in the county, looks like it decreases the number of new cases in that county by about 0.25 people per 1,000, right? So if they have 4,000 people in the county, getting 1% more of the county vaccinated will decrease the number of new cases by one person, right? If I scaled it up that way. Now, it is negative, right? However, if we remember before, if we run this really simple naive regression, where I've got new cases per person was a function of percent vaccinated, we said that the coefficient estimate we see will include the true relationship plus this bias component. So we're going to think a little bit harder about this bias component. And I won't ask you necessarily to put a sign on it, like on a question on the exam, but I do want to like introduce the idea of how you could do this in practice. So first of all, X2, let's say the variable that we left out is income, the average income in the county. Well, the variance of any variable will always be positive. The covariance between percent vaccinated and income, what do you think that relationship likely is? As people or as a county has a higher average income, what do you think is probably true about the percent vaccinated in that county? I see someone pointing up, and what we'll actually see, I'll show this to you in the data, this covariance is positive. But even if I didn't have the income data, I could at least start to think about what bias might exist in that naive regression I first ran. This is what the coefficient would be if I were able to include income in my regression. So this is the relationship between income, the variable I left out, that second variable, and my Y variable, new cases. What do you think is maybe true about counties with higher income? Do you think they're more or less likely to have a higher number of cases? I put it this way, I think I was describing this to a different class, but you know, when the quarantine hit, people who had a lot of money, I mean, it wasn't as big of an issue for them to alter their schedules and quarantine, and maybe some of their jobs were a little bit less likely that they had to show up. So they could stop their behaviors, or they could stay at home more likely. If I'm not making a lot of money, I got to keep hustling, right? I have to go out. I have to go to my job. I have to pay bills so I can continue to live in my house, right? So maybe we would expect that, as income goes up, right? Maybe the number of new cases we see actually goes down. So this effect would be potentially negative. And we can see because we have the data, but if we didn't ahead of time, we could maybe put a sign on this bias and say, well, look, a positive divided by a positive times a negative, my bias component looks like it's negative here. So I think when we ran this regression, we saw negative 0.25. It's likely that I've got some negative bias so that the true effect is actually something that's much smaller, closer to zero. Or maybe it's positive. Maybe the sign flips. Maybe if this is a large enough negative bias, right, my coefficient is really being swayed by that. So I'll go to my data. And the first thing I could do is look at this and say, okay, look, I've got, covariance.p, no, S, because we have a sample. I'm going to select my cases per person. No, not cases per person, sorry. We included as our first X variable, the percent vaccinated. So that was my first variable, comma. What's the relationship between that and the variable I left out, which was over here, median income, right? So I'll select that column, and I already tell you I made a mistake, which is I accidentally selected the labels. So we have to go, we only want to start where the data starts. So I need to start these in the second row. Okay. So this will tell me whether or not my intuition about the relationship between income and percent vaccinated is correct, right? So I hit enter here. Sure enough, this covariance appears to be positive. Okay. So the next thing I need to do is, okay, what if I actually were able to include income in this regression? Well, we can do that as well. However, there's one problem. So I look at this median household income and I go to data analysis, regression, hit OK. I've got my cases per person as my Y variable, But now I want to select household income and percent vaccinated. So I select those two columns of data. Everything's great. Excel's mad at me. All right. So in Excel, unfortunately, it doesn't have the power to move these columns around the background, and it needs them to be right next to each other. So we've got to exit out of this. And it's a pretty simple fix, but it's kind of annoying, which is I'm going to insert a column, and it's really just a matter of any X variables I want to include in my regression, they have to all be right next to each other. So I need to make sure that these two variables are right next to each other. Now, when I go to run this analysis, cases per person was still selected as my Y variable. My X variable, I want to select income and the percent vaccinated. Control Shift, Command Shift on the Mac down arrow. Hit OK. Now, I actually get that regression to run. We're explaining about 12% of the variation in the number of new cases per person with just these two variables. They're both highly significant, right? These p-values are basically 0. And I can think about now, if I look at this estimate, right, negative 0.13. So the new estimate I see is negative 0.13 after I included income in that regression. So once I included income in my regression, I completely eliminate this bias component. So notice if it went from negative 0.25 to negative 0.13, the value of my bias must have been what? Negative 0.12, right? That's what was kind of being added in there before, kind of causing me to see a bias coefficient estimate. Okay? So we could do this. I won't expect you to like put numbers or signs to the bias in the exam, but like intuitively, if I didn't have data on something, I might need to do this. Like I could kind of cheat here because I had the variable that I had left out originally. If I don't have data on that variable, all I can do is tell you like, here's the coefficient I see. If I know the bias is negative, if I didn't have income data, all I could do is say, well, this is the best I could do given the data I had, but I already know it's going to be biased downward a little bit. But the true effect isn't going to be quite as negative, right? And sure enough, it played out when we actually had the data. We could see it wasn't negative 0.25. Once we could control for household income or average income in that county, cut it almost in half. Right? And also we can add in now, this is the effect of getting 1% more of my county vaccinated, holding constant the average income. So two counties with the same median household income, but one of them gets 1% more of their population vaccinated, we would see a decrease in, decrease in the number of new cases per person, about 0.13. Any questions over anything there before we keep moving? Okay. All right, so got a couple more things. So the other thing I wanted to show was, okay, well, I've got all this other information as well, which is like the unemployment rate, whether or not it's a metro, county, and then I have the region of the country. So one thing that's kind of annoying is if I go to run this regression and I try to include, I know there's an issue with this one. So let's just say I want to go from metro to household income. Those are my X variables I want to include, right? I hit OK. I get this line S error. What that means is one of these variables has either a blank or a non-numerical value in it, like a letter. I know what it is because I looked at it ahead of time, but I wanted to show this to you in class if you ever run into this error if you're working in Excel. So I had this data filtered from the beginning. Just a reminder, if I select my entire data set, just using that Control Shift. So if I start up here in cell A1, Control Shift, Command Shift on Mac, hit the over, hit the down arrow, and then click this filter button. That's what adds in these little arrows at the top for me. Notice if I unclick filter, there we go. Okay. So I can look at all the observations for my variables by clicking on that arrow. So I'm going to scroll down here. Everything looks good. Ooh, I got a bunch of blanks. Okay. So what I'm going to do is deselect everything. And I only want to see those blank observations. So here, there's no unemployment rates for these areas. Oh, well, there are these counties in Alaska. The data doesn't come in as easily. Like maybe there's just not as, the populations are relatively low. And so I'm okay because I don't have data for these. I'm just going to delete them, right? They're not usable. I'm not going to, I can't put fake numbers in there. It's missing. So I'll delete those observations, right? Go back so I can see everything again. And now it should be okay. So now I go to regression, the X variables I want to select. I'm actually going to select everything all the way over to kind of the region of the country that it's in. Remember, I can't include population because that was already kind of used to create my Y variable, right? My cases per person. So I'm going to select all of those. Everything looks great. What did I do wrong? Oh, it's because I deleted those. So I have to reselect my Y variable. Everything looks great. Well, what's going on here? Why are some of my p-values screwed up? So anytime that you have something where you have multiple groups, you have to leave one of those groups out. So here I've got region of the country. So the US, right, we have these different regions. Each state is kind of classified in one of them. So I was just trying to use this as some type of geographical control. Well, the problem is these are the only 5 regions that are defined by this US kind of census, the way that it's set up. And so this is the effect. If you're looking at a county in the South, the predicted kind of change in the number of new cases would be -8, but relative to what? Well, it has to be relative to something, so I have to leave one of those regions out, right? So this would be kind of like if I was looking at, the other one I use sometimes, maybe I will look at next class, is I did this thing once where I tried to estimate football revenues. I have a sports econ course, and we were looking at revenues for different conferences and using all this information to try to predict revenues. And we just included an indicator for what conference the university was in, right? Well, the problem is you have to leave one of those conferences out. Otherwise, it's relative to what, right? Now, in football, that one's easy because you can kind of just or in college sports, it's easy because you can leave out like the independent schools, right? But you have to leave one group out. So Excel will do that automatically for you. It's just that if it does it automatically, it screws up the p-values on one of your other variables. So we're going to go back, and the way I have this structured, we're just going to leave out the South, the very last, that we're going to leave out the South manually. So that way it doesn't screw up the p-values on one of our other variables. So we'll select everything except for the South. Down arrow, hit OK. Now everything looks like it's running correctly. We've got our R squared up to about 30%, right, with the X variables that we've included here. And now it's looking like the percent of vaccinated in the county, if it goes up by 1%, it actually increases the number of new cases by 0.04. And it's significant at what levels? Well, p-value of 0.03, I could say that this is a significant positive effect at the 10 and 5% significance levels, or at the 90 and 95% confidence levels. Okay. Holding everything else in this regression constant. So 2 counties with the same average income, same unemployment rate, both either in a metro area or not, both in the same region, whatever region that is. But one of them has 1% more of their county vaccinated. We'd expect to see that their number of new cases go up. So this is kind of weird, right? It's definitely counterintuitive. But this is where we have to be careful with these regression results up to what we're doing in this class. There's still just evidence of correlation. So even though I've accounted for some of these socioeconomic things, region of the country, whether or not it's in a city area, which we think probably has a pretty big impact on the spread potentially. Remember, all these bias components, in practice, it's not just one, right? I was showing you one for the sake of kind of introducing it. But really, if I ran a simple like linear regression where I looked at something like this, then my estimate would actually be, so covariance between x1 and x2, variance of x1, but also any other variable that has a positive or negative covariance, anything other than 0, right, with the variable I included, and anything that would have an impact on Y, I'm going to have like a ton of different bias components here. And my R squared was only what, 0.3. So I was explaining 30% of the variation, which means I'm still not explaining 70% of the variation. So there's likely a lot of other omitted variables that definitely have relationships with my Y variable, okay? And some of them are likely to also have positive or negative covariances with the variable I included. Oops, sorry. So I need to start trying to go out and gather data so that I can include that variable in the regression and then eliminate that bias component. So here, even though we found a positive effect of the percent of people vaccinated in the county on the number of new cases, COVID cases, maybe we're still leaving out some variables that are biasing that estimate, right? I think a good one here would be like temperature or anything like that that might alter behaviors, because not only might we have this what we call omitted variable bias, but what am I maybe picking up here? What it could be true about the percent vaccinated in the county. As a higher percent of the population gets vaccinated in that county, what might happen to the behaviors of individuals? It might be like more likely to like, not wear masks, not distance, go out and do whatever. I know as soon as I got the vaccine, I was like, yeah, I'm done with all this. Like I'm doing whatever I want now, right? Which maybe I've changed that too much. But you see people's behaviors change. So you're probably not picking up the actual effect of the vaccine, but the total effect of the vaccine as well as the change in behaviors from that, right? Now, if we get some type of measure or metric to control for how likely or unlikely people to be out in public, or to, are they increasing how much they're going out and about, which I gotta imagine someone's looked at this, because I think it'd be hard to get it because it's proprietary data, but maybe, I think I've seen like people with Chinese data do this because the government has a bunch of information on it, where you can use your cell phone and they can actually pick up on the geo kind of like spatial, like the movement of people. And then you would actually have a measure where you could control for human behavior and really pick up just the effect of the vaccine there. Well, there's also these techniques that you can use, which are like, maybe some states restricted behavior a lot still. So I could look at like, well, how did things change in this state when they got more people vaccinated versus this other state that had these policies? Look at the difference between those two. There's all these other techniques that after this stats course, you would start to dive into that help you go from, well, just correlations, which are still useful in making predictions, but may not really be picking up a causal effect. So there's some strategies we can use to specifically pick up the causal effect of things. We're not doing it in this class. We don't have enough time, but we have to walk before we can run. You first have to start out, how do we pick up these correlations? How can we make predictions? And that's what we're doing here. Right? So yeah, I don't know. It's very, very useful, right? Like, that statement's pretty strong. Like if you could include a bunch of controls here, you could compare otherwise identical counties. One of them has 1% more of the population vaccinated, and you can pick up on what that effect is. Also, for the sake of transparency, and it's a little bit outside the scope of this class, but I was pretty convinced I was going to show you this, and it was going to be like a positive effect from a naive regression, and slowly work into a slightly negative effect. But I started to look at, there's other ways we can run regression. So one thing that you could do is, cases, so percent vaccinated, you could include quadratic terms, which then allow your line of best fit not to just be linear. So when I actually went and looked at this data, what ends up being true if you include a quadratic term, so this is like new cases up here, is that the actual relationship, let me see if I can remember what it looked like. It was, so initially, it was increasing for really low vaccinations. So like if I'm going from 10 to 11% of my county vaccinated, that additional 1%, it appeared as though the human behavior changes of that 1%, they were going out and about more, but people still aren't vaccinated. So it caused the spread. So you actually saw at the low levels is where you were getting this positive effect from a higher percent of vaccinated individuals. But eventually, once you get to these higher levels, right, then getting more percent of your county vaccinated, yeah, people are changing their behaviors, but it doesn't matter now because there's more people that potentially are, not as likely to get this disease. So it wasn't a linear data set. Like the data did not look linear. So when we were forcing it to be a linear relationship, we were getting some kind of, that positive effect that doesn't make a lot of sense. But if we allow for a quadratic term, what we see is that, yeah, when you have a low percent of your county vaccinated, just getting 1% more vaccinated is probably not going to be helpful because the additional people vaccinated will take on behaviors that are a little bit more risky, or maybe even the people around them perceive it as though more people are vaccinated, so they're being riskier too. But you haven't even gotten close to maybe this threshold, this kind of herd immunity idea. And so once you get to a certain level of vaccination, then increasing that percent of your population that's vaccinated does start to actually decrease the number of new cases. Right. So just to be fully transparent, that's kind of what that relationship looks like. But it's a little bit outside the scope of this class. I figured it would be more linear, but it ended up being kind of a quadratic relationship there. So, okay. Any questions on that before I kind of let you guys get out of here a little bit early today? So what I want you guys to do before we leave, I could have sworn I had it pulled up. Well, let's go. On your way out, just kind of give me and your response. I'll give you 10 out of 10 for the day. This will be the last time I use iClicker, so I'll go in, drop your lowest. Like I said, I can't remember what the syllabus says. It's either 2 or 3 scores. Post what your kind of iClicker grade is, kind of across all of the different days that we've used it, and get that up on Canvas before next class. I'll also be putting up a couple, 1 or 2 PDFs. Actually, I'll be putting up 2. They're papers that use some pretty basic linear regression that I want to kind of show you how it's being applied in real life. And I think the topic is kind of fun, kind of interesting. We'll go over that on Wednesday as well. I'm not expecting like you read through them at all. It would be helpful. It would be an more interesting discussion and probably assist with your learning if you at least read like the intro and conclusion to get an idea about what the paper is about. We'll kind of use those as a tool to kind of see how we actually apply this stuff in real life. And then, like I said, towards the end of class, we'll probably do a little bit of exam review. So on your way out, make sure you answer any letter here for the iClicker to get the full 10 out of 10. This will be the last day we use it. Other than that, there's no questions for me. I'll see you guys on Wednesday.